Hi everyone, this is John Wen. Today is July 15th, 2020. In today's video, I'm going to go through the updates of the research items since the past week. So you can see from here, I still have 2 items in the stack in the list. So for the first one, to extend the survey to the journal version, I estimate the progress is about 5%. And the second one, deep learning workflow, I estimate the progress about 4%. So let's get into the detail. For the extended survey to the journal version, as suggested by Dr. Liu, I refined the DBDS-B algorithm on its pseudocode to according to the original paper. I think that way might be better. And then I also use a add new command which creates a variable in the LaTeX document and to replace all the scientific workflow management system or scientific workflow management systems and for all the occurrence in the paper. And currently I'm working on the subsection 5.4.1, and basically this is a challenge of the cloud performance fluctuation. So I think here is a typo, but we can change that later. Let's take a look at the paper currently. So currently I'm working on the section of the 5.4.1, and this is about cloud performance fluctuation. And because of writing this section, I also refer to several other papers in order to understand more about what is going on, how people handle, or what's the kind of issue that's occurring right now for the performance fluctuation. For example, I found one paper that is very good. This paper 4, which name is a view of the cloud computing, and this one has more than 10,000 citations. So I think it's a widely accepted paper, and it describes the fluctuation on the I/O as well as the network access. So I think it gives a very good or very clear statistics. So I think that's very persuasive if we cite this paper as well to introduce the problem we have. And also, I think currently the most way to deal with the fluctuation or the performance variation is based on the dynamic scheduling. And further, I think the performance prediction is a big part to help the dynamic scheduling be more precise or be more proactive. So that is one thing. I'm currently reading the papers from the DBLP, and basically I'm searching the cloud performance prediction or the workflow performance prediction. The cloud basically, I think in the workflow domain, there's not too much work on working on the performance prediction about the cloud or the hardware. So I only search the cloud performance prediction. I think there's not too much work either, but there are several papers that have been covered this topic. For example, like this one. This one is a performance prediction in the dynamic clouds using the transfer learning, and I think this is published, I believe, in 2019 or 2020. So most of them are quite new, and this paper is aiming to learning a performance model about the cloud service. Basically, it wants to improve the efficiency or learning efficiency by keeping some already learned structure. For example, some layers they don't want to change, but based on the feedback or based on the new status of the execution or the performance, then they want to change the model only partially based on the prior model. So that is called transfer learning. So currently I'm reading this paper, and I try to gain some insight and maybe see how the improvements can be done to improve the the prediction on the performance variation on the cloud in the cloud. So basically, I'm also checking other papers. I think I'm still working on that and try to make this section that's richness as well as correct and accurate. So this is the part I'm working on currently for the paper. And let's get back to the slide. And so the second item is a deep learning workflow. I think I read the code presented last week, the simple CUDA neural net implementation. I think that code is too simple and maybe it's also problematic in the implementation. So basically you can see from this model or from this code, they only put the sigmoid layer and also they directly do the forward propagation and back propagation with delta. Basically this is the method to calculate the derivative. So basically because they only have one layer, so they don't need to do the derivative chain, so they don't need to care about the back propagation. So this is a very oversimplified model, and basically then they just do the dot production, the dot multiplication between the matrix, and then they can get out the result. So I didn't see, I think this may be a training process. I didn't see the testing, so I think this is a partial work. Also, I refer some further works and many other works. For example, I find one that is a CUDA implementation on the neural network. I think this is a very good one, and basically this is based on the CUDA C++ instead of CUDA C as the last one presented. And this one, it has a linear layer, ReLU layer, and linear layer, and then sigmoid layer. It has two separate methods to do the forward propagation and back propagation for each of them. So I think that's more extensible as well as more close to the practical utilization and implementation. So I think I'm currently reading through this one, as well as it includes the source code in the GitHub. So I think I can look into and see if from what I learned, I can write on other layers, for example, like the neural other layers, and to include in the neural network by CUDA. Furthermore, since I'm not quite familiar with the C++, and for this example, they utilize CUDA C++, so they are able to have many classes, and they are able to do many polymorphism, and I think that is good, because a neural network is a very complicated model, and maybe this is a proper way to implement. So I also learned some C++ syntax to understand the code. I'm currently reading source code as well, and hopefully can get better understanding and insight soon. So let's get back to the slide. And also I focus on learning process as well since the last week. This week I go through the memory access pattern, and basically in CUDA there are two kind of access pattern, and first one is called align memory access. Basically it occurs when the first address of the device memory is an even multiplier of the cache granularity. So you can see from these screenshots, there are two cache granularity based on how we utilize a cache. And the first one is 128 if we utilize L1 and L2 together, and this is called cached. Basically it's cached memory access, but this on this side is 32 byte transaction, and basically it only utilizes L2, and but it has better granularity if we want to do more fine-grained scheduling or fine-grained execution. This will be the better one. So based on this different cache granularity, the choose or the scheduling on the access pattern will depend. So basically, this one is basically we are able to see some difference if we are choosing the different cache allocation or the cache access. So basically this is 2, but for the global memory writes, it only supports the L2 type of the granularity or the type 2 access. So the granularity will always be 32 for the memory writes. And I also look into the ASO, which stands for array of struct, whereas SOA, which stands for the struct of array. And basically the difference is that the memory, the bandwidth of occupation is different. The AOS is taking more bandwidth, but it's underutilized bandwidth. So basically it's only access half of them, but it takes more than what they need. But for the SOA, it takes consecutive memory access, so that will be better normally in the implementation in CUDA. So this kind of implementation will improve the performance. So I think that's pretty much for the last week the updates. And besides these two, I also reviewed the paper, and hopefully can be done by today, because today is also the deadline. And so I think that's pretty much for today's updates. And thank you so much for your time for watching this video, and hopefully you enjoy it. Until next time, happy coding.